Hello, and welcome to this MCMA webinar titled Discover a Novel Approach to Control of Precision Linear Motor Gantry Stages, presented to you by ACS Motion Control. I would also like to officially announce that the MCA will now be the Motion Control and Motor Association, MCMA. In June, the Motion Control Association, MCA, and the Motor and Motion Association, SMMA, completed a merger to become the new MCMA. Over the coming weeks, you will notice updates to our website, webinars, newsletter, and other email correspondence that reflects our new name and logo. For more information about the merger, please visit our website, www.motioncontrolonline.org. My name is Liz Wright, and I'm the Marketing Manager for the Motion Control and Motor Association, MCMA. This webinar will be recorded, and an email with a link to the recording will be sent to you within the next 24 hours. If you have any questions during the webinar, please submit them via email. I'd now like to introduce our webinar presenter today, Jason Gorgas. Jason Gorgas is the General Manager for ACS Motion Control. He received his bachelor's degree in electrical engineering and minor in business management from the University of Minnesota. Jason went on to receive a master's degree in electrical engineering from Arizona State University. Focusing on digital signal processing and control systems, after working as an engineer at Honeywell Flight Control Systems, Jason joined ACS Motion Control in 2007 and currently resides near Minneapolis, Minnesota with his wife. He enjoys spending time with family and friends and being active in his local community. This webinar is sponsored by the following companies. ACS Motion Control is a world-class provider of high-end multi-axis motion control systems. ACS products are uniquely designed to meet the needs of equipment manufacturers with the highest throughput and highest precision requirements, such as semiconductor wafer inspection and metrology equipment, flat panel display manufacturing equipment, electronic assembly equipment, and more. Founded in 1985, ACS Motion Control's core competencies include servo algorithm development, real-time operating system development, advanced electronics design, Windows-based user interface design, and technical support of demanding motion control applications. ACS's international headquarters is located in Israel, and application support and technical sales offices are located in the U.S., China, and South Korea. Micromo. Since 1961, Micromo has provided the widest range of high-precision rotary and linear custom motion solutions to markets such as medical, defense, and robotics. As a member of the global Faulhaber Group, Micromo brings together cutting-edge, high-performance, and energy-efficient products and technologies from around the world, such as brushed, brushless, stepper, thin profile, piezoelectric and linear DC motors, encoders, and gearheads to the North American market. Decades ago, it started with the Faulhaber coil, the landmark invention that paved the way for the DC motor market. Today, Micromo partners with customers to help deliver innovation to market first. Thank you again to all our sponsors. Now I'd like to hand it over to Jason.
Okay, thanks, Liz. All right, so I'll go ahead and get started, and thanks to everybody that's attending the webinar here. I'll start with an agenda just to review what I'm going to cover in today's presentation, and then we'll jump right into it. So as Liz introduced, the subject of the presentation today is a unique or a novel approach to control of precision linear motor gantry stages. We're going to start out by talking about some of the performance requirements that we at ACS see for applications that employ these types of stages, and then we're going to talk about some specific applications for these types of systems. I'll describe some of the factors that affect performance in those applications. Then I will go through a brief summary of a traditional motion control solution for that type of application and what are the limitations of it. And then I'll present actually the new solution that ACS and some other companies are working on developing for this type of application based on today's latest technologies, and we'll talk about some of the capabilities of that type of a solution in case anybody listening is interested in that type of a system. And then I'll finish up with some conclusions as well. So let's go ahead and I'll start with the performance requirements. So when I or we at ACS talk about a precision or high precision linear motor gantry stage or system, high precision from our point of view is actually talking down to the nanometer level in today's most demanding applications. So examples of requirements from the application that eventually justify the use of this type of stage would be, you have to move and settle a device, might be an inspection head or a printing nozzle. You have to be able to move and settle with accelerations upwards of 2 Gs or more, velocities on the order of 2 meters per second or more. The actual motions for these types of move and settle moves are, can be very short, from submicron if you're moving just to different locations on a single die. In a semiconductor application to, of course, very long moves that can be on the order of many millimeters or even up to meters or more in length. We also talk about settling windows for these types of applications. So if you move from point A to point B, the settling window actually defines how close do you have to be to point B in order to consider the motion complete. And in applications we see today, we see settling windows on the order of plus minus 50 nanometers as the maximum allowable error, or it can even be less than 50 nanometers. And then settling time actually defines once we've commanded a motion to move from that point A to point B. There's a theoretical amount of time that it takes to do that motion, but then in the real world, it generally takes a little bit longer than that theoretical amount of time. Based on Newton's laws, because you also have to settle into position, which is where the servo algorithms come in. And so settling time is very important, and some of today's applications demand a settling time of a few milliseconds, even down to effectively zero settling time, which means that you finish the actual motion in the same amount of time as the ideal motion. So very demanding move and settle requirements. Another important requirement for this type of application is the idle position error, or the following error or position error when the stage is being controlled but not in any motion, when the velocity is zero. This is often called jitter. And the idea here is that when the servo system, the control system, is holding the motors in place, you need that jitter to be very small so that whatever is being done, which is typically a measurement, whether it's an inspection application, metrology, whatever, that measurement, the resolution of that measurement depends on the jitter, which is a function of the control system. So, today's windows for inspection and metrology applications for jitter, we're talking even less than a nanometer peak-to-peak error. So very, very demanding, and of course that then requires even a high-resolution feedback device to even resolve down to that. To that level of positioning, but that's outside the scope of this presentation. But certainly that's a whole subfield as well, talking about the type of feedback technologies required for resolving that level of position accuracy and precision. Also, spectral density is often specified as an important requirement, actually defining how much of the error. If you look at the error not in the time domain, like looking at what is the error as a function of time, but rather in the frequency domain, what spectral components or what frequency bands carry the majority of the error magnitude, that also can be an important important requirement and an important spec. for an OEM, and that kind of varies depending on the application as far as what frequency ranges or frequency bands can tolerate the error. And then the smoothness of the motion while you're actually moving, it's usually during a constant velocity type motion. You might be scanning one of the axes and doing something while you're scanning, and again, that could be taking images, doing some sort of metrology measurement. It can also be something like printing if you're doing direct laser right lithographic printing. That also can be done during motion, and so for that type of motion, the important requirement or the important specifications are how close to the ideal velocity can you get, or how smooth is the actual motion. And so the velocities, of course, can range quite widely depending on the process. It can be very slow on the order of, microns, tens, hundreds, or even less microns per second, or of course on the high end it can be in the hundreds of millimeters per second, or even meters per second, really. So to determine how smooth the motion is, we actually look at what is the following error, which basically we're just looking at the encoder to determine what is the following error during the motion. But another measure is actually to look at what is the amount of time that elapses when you move from one part of the encoder to the next, or let's say when you travel one full cycle of the encoder. And generally, when you're looking at the time or the differences in time by covering some fixed amount of distance when you're moving, the performance requirement or the specification is given in terms of percentage, and a 1% deviation is actually quite a demanding spec. You can imagine as you look at shorter and shorter distances that percentage becomes more difficult to achieve. So for very high performance, high resolution applications, 1% and below can become a very demanding specification to meet. And then I have a note at the bottom that actually, these performance requirements or performance specifications I'm talking about here, they can be measured actually at the motor or the encoder, but it can also be measured at the chuck if it's a wafer or semiconductor application, or the device under test, which if you want to measure the performance, at that device itself, then you're looking at a different type of feedback sensor as well. Typically, that's done with an interferometer. So that can also even make the performance requirements more demanding. What you see on the right side of this slide is an example taken from an application where we were controlling a stage. You see a single axis here where in red you see the commanded position during a step profile as a function of time. So the red is the nice smooth step plot, and then the yellow is actually the feedback looking at the encoder. What was the actual motion during that series of profiles? And you can see that actually these are very, very small steps, 1 nanometer steps, and so the following error needs to be very, very tight and very precise, very close to the commanded motion. And you see that in this case it's a plus minus 0.4 nanometer peak to peak following error during these motion profiles. So that would be, something common for one of these demanding applications. Okay, so next I'll just do a brief summary of applications. ACS, we have some expertise in certain types of applications. Certainly there are other applications as well, but what we at ACS have experience with are advanced semiconductor inspection and metrology applications. So it can be inspecting a patterned wafer. It can be inspecting a lithographic mask. It can be inspecting a flat panel display as well. And there's different technologies for doing these types of inspection or metrology measurements. E-beam is arguably the leading technology for wafer and semiconductor and mask inspection. There's also scanning electron microscope and focused ion beam techniques. There are high-resolution optical inspection applications as well, and then also X-ray, which allows you to actually view, of course, inside of the materials and look at defects not only on the surface but also throughout the entire material, which is important for 3D 3D system on chip applications. Lithography itself, actually the process of generating masks for wafer manufacturing, lithography is also a large field of sub-applications for high precision gantry, linear motor gantry stages, and then some of the technologies there, again, E-beam, deep ultraviolet, or extreme ultraviolet is kind of the cutting edge today. Technologies for lithography, and also there's direct laser writing, which is also a type of, or it's a type of maskless lithography, which is becoming more widely adopted. And then also we list wide format printing and scribing applications. So printing and scribing are two separate processes, right? Printing is actually the depositing of material onto a device, whereas scribing is actually typically the use of a laser to cut or to make marks or channels on a material. And printing and scribing, of course, can be used in a variety of vertical markets, not only semiconductor but also solar panels and the more general flat panel display or mobile device display market as well. Okay, so next I want to start talking about what are the factors that actually affect the achievable performance in these types of applications, right? So what actually limits the control system from achieving the desired performance? So there's a variety of factors. Resonances are probably one of the most easily recognizable by the control system. So the stage, a stage itself, a stage which a linear motor gantry stage consists typically of an X and an X prime and a Y linear motor axes, or Y, Y prime and X, whichever configuration is needed for the application. And all of those axes have their own resonant frequencies. So the stage mechanics themselves have resonant frequencies. The frame or the base, the platform that this motion system sits on, which is often made out of granite and might be sitting on either a passive or an active isolation system, that frame actually has its own resonant frequencies as well. And I would say a lesser known and lesser studied resonance in these types of systems, but one that we at ACS have been focusing on more recently, is actually the cabling. Right, so when you have a linear motor system, linear motor gantry system, and linear motors in general, right, you have to run the motor and encoder cables out to from the linear motors to the drives or to the control system itself. And when you have these linear motors stacked in a gantry configuration, or it could even be a non-gantry configuration like a more simple XY, you have to route those cables from their exit point on the motor itself all the way out to the control system, which typically exists in a cabinet. And those cables actually have a resonant frequency themselves, and it turns out that they can be pretty important in impacting the performance, and I'll touch on that more later. So a little bit more on the stage mechanics. I mentioned resonances already, so resonant frequencies, but in addition, there are non-idealities that any mechanical system has to deal with and has to try and overcome or minimize. And so those can be, what is the type of bearing, or what sort of friction do you have? Is it linear friction? Is it nonlinear? Generally there's both static friction and during motion friction. So these can be pose a challenge for the control system, because they make the mechanics basically look like a nonlinear system, even though the control system is trying to control it as a linear system in most cases. The cogging, actually, so the linear motors themselves, iron core motors will generally suffer from some level of cogging, which represents a ripple in the force constant of the motor as you move. Ironless motors generally have less cogging or are free of cogging, but even ironless motors might have some residual amount of cogging that becomes noticeable when you're talking in terms of resolutions on the nanometer scale. So the repeatability of the stage mechanics, right? So there's always going to be some level of non-repeatability that the control system has to deal with, and then orthogonality and straightness. A gantry system consisting of an x, x prime, y. You have to deal with what is the orthogonality of the x and the y. How orthogonal are they? Because a real system never can be perfectly orthogonal, so that non-orthogonality can pose challenges for the control system, cross-coupling of the axes from one servo loop to the other, and then also the straightness of the rails and the straightness of the axes themselves, again, are not going to be perfectly straight, and so very, very small deviations in straightness become noticeable when you're talking this level of precision. The stiffness, I guess, is maybe a more general property of the stage mechanics itself, but the stiffness has to do with the resonant frequencies and making sure that they occur at relatively high frequencies, so stiffness is certainly important as well. A few comments on the encoder, the feedback device itself. Right, the alignment of the encoder read heads actually is important, and encoder manufacturers, of course, have tools for optimizing that alignment so that the encoders, generate signals that are as ideal as possible. But even a ideally aligned encoder might suffer from some level of gain, phase, or offset compensation requirement from the control system, meaning that the amplitude of the output signal or the phase or the relative offsets to 0 volts or to ground of the encoder signals might not be ideal, and so the control system may need to compensate for those. And then there's noise. Electrical noise is generally generated by the control system or by the drives, and so that noise is it's generally picked up by the encoder cables, and any noise that you see on the encoders corresponds effectively to a disturbance in position measurement. So that certainly poses a challenge for the control system as well. The image that you see on the right of this slide actually shows a frequency response measurement or a Bode plot for anyone listening that's familiar with Bode plots and frequency analysis. But it's designed to basically show the electromechanical signature of a single axis, or it could be a multi-axis system, where we are plotting what is the overall gain of that system. And we look at that as a function of frequency, starting at low frequencies on the left, going to high frequencies on the right. So this is actually taken from a tool that is one of our tools in our software environment that we use to optimize the performance of motion control axes. Okay, so actually here I'm going into a little bit more detail about these factors that are affecting performance. So of course the control system has a huge impact on the performance, and that's ACS's specialty, of course. So the servo algorithms themselves have a big impact on the achievable performance. So PID is the well-known traditional classical feedback type control. That's I would say the standard in most of the industry, most of the motion control industry. But a growing number of companies are adopting adaptive or state space type control algorithms, ACS being one of those companies. And so the power of that servo algorithm and its sophistication is has a huge impact on the performance. And then the sampling and update rate, actually, almost every control system and amplifiers that you'll see on the market today are using digital control, certainly for the position and the velocity loops, and also for most amplifiers in the current loop as well. The rate at which you can sample that information and process it is important, and of course, the faster the rate, the more information you have, the better you can control and the higher bandwidth you can achieve. So those are important specs to look at if you're considering a motion controller or a servo drive or amplifier. And then the profile generation is generally also handled by the motion control system. So the servo algorithms deal more with, given some command, how do we make sure that the actual system is following that command? Whereas profile generation, or the process of generating the command, the motion command, that's also an important process, because when you're talking about short moves, short point-to-point moves, which is common in a wafer inspection application, for example, how you generate that move is very important. So, a very common method would be, a second or a third order point-to-point motion profile, where you specify, what is the maximum allowable velocity, acceleration, and if we're talking jerk, then also, or talking third order, then you also specify the jerk. Third order profiles, I would say, are fairly common, but some controllers, ACS again being one of them, offer even more advanced profile generation capabilities, where it might be doing even much higher order profiles, or profiles with specially designed shapes designed to minimize following error. So it might not be so easy to recognize the difference to the human eye. What is the difference between a third order profile and a higher order profile, or a specially designed one? But those small differences can be really important in terms of how the servo response of the control system is. Okay, and then the electronics itself. So when I say electronics, I'm actually talking here about, of course, the electronics in the motion control system, and that's primarily the power supply and the drive, or the amplifier. I guess I use those terms somewhat interchangeably. So the power supply ultimately is responsible for taking an incoming power signal, right, which is typically an AC voltage, and generating a, let's say, a clean power signal that can be used by the amplifier or by the drive. So how let's say, clean, or how constant that power signal is to the amplifier is very important. So actually in the diagram here you see an example of a power supply that generates a bus voltage for an amplifier. And so how constant that bus voltage is, if that supply is outputting a 100 volt DC bus, then obviously we'd prefer that 100 volt DC bus to have a very small ripple, maybe on the order of a few millivolts, as opposed to tens or hundreds of millivolts. So the power supply electronics are important. The drive, the quality of the drive, or the linearity of the drive itself, is also very important. So given some command to the amplifier, the purpose of the amplifier is to take an input signal and generate a scaled up version of it, right, an amplified version of the input signal. But no amplifier in the world is perfect, and so any input signal that goes in, the output signal is going to have some level of distortion. It might be some distortion that occurs more noticeably with small signals versus large signals, but in general, that measure of distortion or linearity, that's a very important measure of the amplifier. I mentioned before that most amplifiers used in the industry today are digital amplifiers, which means that they have to take real-world information that's provided from a feedback source, or also when we're controlling a motor, we actually control the current in a motor. So those, the current needs to be converted into a digital value that can be processed by the control system. And so the process of actually taking the analog signal and digitizing it, that's important as well. And that process, has an associated amount of distortion or injected noise associated with it. And the amount of noise, the quantization noise that occurs in that process, is a function of the resolution of the A to D chips that are used, or the analog to digital resolution. And then also the signal to noise ratio is an important contributing factor there as well. The last point I'll make for the electronics is also how much generated noise, or how much noise does the amplifier generate itself. And actually it can be the amplifier and the power supply. Both of those components can generally have switching components inside of them, typically transistors or FETs. And those those switching transistors are going to ultimately generate noise, and so the amount of noise that's generated there is an important factor, because it can ultimately go into the encoder and affect the position measurement, and it can also affect actually the current that's going through the motor itself. So we have a diagram here that shows some of the impact of these different these different effects, whether it's noise that's coupled capacitively, whether it's noise that's going through ground loops, whether it's noise that affects ultimately the voltage of the encoder signal. All of these sources of noise can degrade the ultimate performance of the system, because they effectively make it a nonlinear system. Okay, so next I'm going to talk then about what's a traditional motion control solution. What have we at ACS and others that we know of and customers that we've worked with, what is a way to solve this challenge of controlling a high precision linear motor gantry system? How has that been done generally up until now? And the way that that's done generally is that you have a motion controller, right? And the motion controller communicates to typically a host computer, a host PC, but it can also be a PLC or maybe a more simple HMI touch panel. But the motion controller itself, from the motion point of view, has the responsibility of generating the profiles, and it also has, in many cases, the responsibility for handling the position and the velocity control loops. So that means that when you have this linear motor gantry system, which we just have a stock image here showing an X prime, and then actually here you see two different cross axes, two separate carriages. So when you're controlling a system like this, as it's drawn here, we just show 3 amplifiers, but you have the feedback sources from the X prime, and let's just assume that this is a single cross-axis Y. Those feedback signals would then go actually to the controller, right? Because the controller takes the position feedback, and it also generates from that the velocity feedback and uses that to close position and velocity control loops. The output then of that controller would be current commands for actually what current is required to go into the motor to generate the necessary motion. And because on the last slide I mentioned the significant impact of PWM or switching noise on encoder signals, on motor current, for very high resolution, high performance applications, PWM switching actually becomes a non-starter for many of these applications. So even though PWM drives are widely used in the industry, and ACS also produces a wide range of PWM drives, linear drives have often been used for the real high-end applications that can't tolerate that switching noise because of the process, or because it just induces non-idealities in the system that degrade performance. So linear drives are commonly used for these types of applications, where they take the current command and then they ultimately provide the power to the motor through the motor phase cables. So in this type of system, the motion controller and the linear drives, they are generally housed in their own enclosure, or it could be in a rack or a control cabinet. Those are typically all sitting together, and then you have the cables running out to the actual system itself. And then you see a note on the bottom that, again, linear drives, the idea of a linear drive is that it doesn't suffer from switching noise like a PWM drive. So that's a traditional motion control solution for these types of high precision applications that ACS has provided and other companies have provided for many years. And then if we look at this more from the hardware point of view, less from the architectural point of view, but now from a hardware point of view, if I show an example of a controller and then some drives here that would be sitting in a cabinet, right? So you have the controller which is communicating with the drives, and that might be done with network communication, or it might be done with discrete, analog even signals. and then you've got a power supply here that's providing both the the logic power for these devices, but also the power that's ultimately used to generate the power that goes into the motor, right? So the bus voltage. That's generally all sitting in the cabinet or in an enclosure or a rack, like I said. And then you've got these long cables here, which are represented by the blue and the green, which are the motor cables and the encoder cables, right? So these are the long cables that have, multiple conductors inside of them. For the motor cables, they're larger conductors. For the encoders, it's smaller conductors. And those are the ones that are going out and go out through the cable tracks and ultimately are, of course, terminated at the motors and then the read heads of the encoders on the gantry system itself. So, I mentioned already that the encoder cables and the motor cables, this cabling and the associated cable management system on the gantry system, that's actually a contributing factor to performance degradation because of the resonance of those cables, and because they're moving and they have different properties depending on the resonant frequencies change depending on where you are on the stage itself. So the next slide here is basically, I guess I got a little bit ahead of myself in describing those limitations. But again, these moving cables oscillate. They oscillate at generally low frequencies, which poses a problem for the control system. You generally want to avoid having resonant frequencies within the bandwidth of the control system or within the servo bandwidth. And as I mentioned, that frequency is generally changing depending on where the where the motors are. There are tricks for trying to eliminate the effect of resonances on a motion system. One of those tricks or one of those methods is called profile shaping, or sometimes called input shaping. That's a method where you actually change the motion command itself to try and move the axes in such a way that you don't excite resonances. But that's not a suitable approach when you have low frequency resonances, because that approach actually extends the amount of time that the motion itself takes, right? So the idea is that you command a slightly longer motion in order to not excite the resonances. But when you're talking about very short moves, short point-to-point moves on the order of milliseconds, then using that approach might actually take a 10 millisecond move and it now becomes a 20 or a 30 millisecond move, which certainly is not acceptable. And increasing acceleration also is generally not a suitable way to overcome that limitation, because by increasing your acceleration or your jerk and in general your motion profile parameters, just moving faster, you actually generate more oscillations, and so you might actually end up with a shorter theoretical move, but when you take into account the amount of time it takes to settle into your desired position, the end result actually gets worse as you start increasing your motion profile parameters more and more. So the cabling has some real limitations, or some factors that limit the performance. And then the other one I had also touched on briefly was the drive technology, right? So linear drives, linear drives, they have the nice benefit of not having the PWM switching noise, but linear drives by their nature are relatively inefficient, right? They don't use switching transistors, which are very efficient, but rather they use transistors that are operating in the active region or during the always-on region. So they're always dissipating heat. And if you look at any linear amplifier, whether it's an audio amplifier or a motor amplifier, if it's a linear amplifier, you typically see a heatsink, and you might even see fans as well. And that's just because the fundamental physics of a linear amplifier inherently has some heat associated with it that needs to be dissipated. And as a function of the need to dissipate that heat, that type of amplifier is generally pretty large and pretty heavy compared to a PWM alternative. So there's benefits to linear amplifiers and benefits to PWM amplifiers, but for these real high precision systems, the linear amplifiers are generally used, but the linear amplifiers, of course, are by nature not suitable for being distributable. And so we at ACS have actually developed a line of products called Nano PWM, where Nano PWM is actually it's a revolutionary new design of a PWM drive that actually has the same level of performance as linear amplifiers. So it actually addresses the challenges of a PWM amplifier for high precision applications, which is to be able to achieve the real fine performance down to the level of nanometers, such as avoiding noise generation, that sort of thing. So we've developed a product like this, and as far as we know, it's fairly unique in the market. This is a fraction of the size of linear drives just because it's a PWM amplifier. We've released multiple form factors of this type of product, but the one I'm going to focus on here is actually one that's designed to be mounted on moving stages itself. And it comes actually, we've developed them in single and dual axis form factors. Now, I'm not really going to go into too much detail on Nano PWM or on that technology. We've actually done previous webinars with the Motion Control Association, or I guess MCMA now, on that topic, and so I would invite anybody that's interested in that technology, please, to either check out ACS website or the Motion Control Association website for webinars on Nano PWM technology itself. Okay, so now we're actually getting to really to the conclusion of this presentation here, which is a new type of motion control solution for a precision linear motor gantry system. And what you see here is an architecture where we have a motion controller that, like before, it's communicating to a host computer or a host PC or other device, like I said, PLC or HMI. But the motion controller actually is physically distributed from or physically separated from the drives. And our network of choice for communicating to amplifiers is Ethercat, and we actually then send the motion profile out over the Ethercat network, and then the drives receive those commands and actually handle all of the servo loops locally, and then those drives actually have the direct interface to the motor and the feedback devices. And as I mentioned, we've developed drives, these Nano PWM drives, in both dual and single axis form factor, so that a single box can run either two or one linear motor directly. So where that really, where I hope that you see the uniqueness of the solution is given on this slide, where actually, as opposed to the previous, the traditional approach to this type of application, where you've got the controller and the drive sitting in a cabinet, and then you've got all of these encoder and motor cables running out into the machine and into the gantry system. Instead of that approach, what we now are able to offer with these Nano PWM distributed amplifiers is to have the controller, which is a relatively small box that's just responsible for logic processing and generating profiles and monitoring the system. That controller actually is communicating out to the drives with a network cable. Right, so it's actually just a Ethercat uses standard Cat5 or standard Ethernet hardware. So you've just got simply an Ethernet cable that's running out to the drives, and the drives themselves are then mounted onto the stage. So the idea is that you have one drive which is responsible for controlling two axes, and that drive is mounted on one side of the gantry where it's right next to one of the motors, and then you mount or then you route the cables from the other motors to that drive. So those cables are never moving. It's static, the connection from the motors to that drive. And then to control the cross-axis, or it could be multiple cross-axes, you have then the single-axis drives mounted on the moving carriages. So the only moving cables in this case is the network communication cable and the power supply the power supply cable that ultimately is used by the amplifiers to generate the power to the motors. And so that supply cable is just a DC voltage, right? It can be a single DC voltage, or it could be a pair of DC voltages where one is lower voltage, 24 volts typically for logic, and another voltage is higher, so 48 or 96 or 100 volts for actually powering the motors. And again, this is very unique in that there are other distributed drives available on the market today, but not drives that are being used for this level of performance type of application down to nanometer level, where traditionally a linear drive or a very high precision control system is used. And a side note that these moving cables, it's even possible to remove those small moving cables and replace them with slip rings or slip bars to completely eliminate the moving cables from the system. So that is the new control solution that we have presented to the market, and I now just want to give a few more comments about the capabilities enabled by that type of solution. So one of them is that by controlling the gantry, the X and the X prime axes together from a single drive, we can offer a unique type of multi-input, multi-output control, where instead of controlling the two axes independently, X and X prime, we actually control it as a single system, where we control the linear motion or the X motion, and then we also control the yaw, which is the displacement between the two sides. And it turns out that controlling a gantry in that way offers a lot of benefits from the performance point of view, primarily because the two servo loops are decoupled and independent from one another. It's also possible then to use the cross-axis position to compensate or adjust that control algorithm as well. So if you have a large moving mass, that of course impacts the dynamics of the gantry system. And that type of control algorithm is suitable for flexible and for stiff gantry systems. So traditionally a gantry system you design like this as stiff as possible so that you can mechanically design the resonances to be relatively high frequencies. But by controlling a gantry system in this way with multi-input, multi-output control, we're actually able to get the same level or even potentially better performance by having a flexible gantry, where it's designed to have some flex between the two linear axes, the X and the X prime. So that actually makes it potentially easier for the mechanical designer as well to employ a control system like this. And as I said, that's enabled by having these multi-axis drive form factors where they control the multiple axes actually as a single system and not as independent axes. So the advantages from the servo point of view, the control point of view, is higher bandwidth, better stability. You can improve the accuracy and then ultimately the repeatability of the mechanical system. It's easier to tune, right? It's easier to actually tune this system as a linear axis and a yaw axis as opposed to a mechanically coupled X and X prime or Y and Y prime. So the tuning is now simplified. And actually you also increase the mechanical reliability and the longevity of the system itself, right? By running it this way, we're effectively running it to be mechanically optimal at all times, as opposed to forcing it to try and be straight when the mechanics aren't actually straight. So it even improves the longevity and the lifetime of the mechanics. And again, I'm not going into detail on any control algorithms ACS offers for gantry systems, but we actually we provide more details about that on our website there. So there's a link to that there. All right, and I'm just about finished here. I think a couple more slides, but I want to also talk about the capabilities in terms of actual achievable performance, right? So by reducing the cost and the length of these cables, we effectively eliminate the motor and encoder cables, except to just get from the encoder to the motor to the drive, which is located very close. So by using just Ethernet and DC power cables in the system, we now make the cabling much smaller, much easier and less expensive to do cable management. And also those cables that remain, they're much smaller and generally are resonating at much higher frequencies because of their lower mass, right? So that's really important, is that those cables that remain, if you choose not to use the slip ring or slip bar to completely eliminate them, those cables will still resonate, but they resonate at much higher frequencies, and so the control system is able to achieve much higher bandwidths because of that. And then the profile shaping or the higher accelerations, those are now possible because of that reduced weight or reduced moving mass. And then you also don't have to worry about residual forces on the stage. Anyone that's worked with a stage that has a fair amount of cable management might be familiar with. The cable management itself might actually, when the system's not under control, the cable management might drag the system to some default position just because of the flex of the cables, and they're mechanically want to be in their optimal position or equilibrium position when it's not being controlled. So now you don't have to worry about having that residual force based on the cable management. Okay, so the last point here is just to actually show the data that we've seen and what sort of performance improvements we've seen by employing this type of distributed approach. So these are just numbers taken on an actual wafer inspection stage doing a 25 millimeter move. So we were actually recording here what is the amount of time it takes to move and settle into position, where we define in position being a 50 nanometer window, and then also we looked at the same data but with a 10 nanometer window. And so with a traditional solution, the best possible performance in terms of move and settle time was we saw 110 milliseconds for the higher window, and then a little bit longer for the smaller settling window. But you can see with the new solution, by putting the drives out on the stage itself, we can significantly cut back that settling time. So 30 milliseconds here, I mean that's you're talking 20–30% improvement. So that's huge, right? Because these machines ultimately are measured. If you're talking semiconductors, these are measured in terms of wafer per hour. So if you can improve wafer per hour by a significant percentage, then you're increasing the value and the return on investment to your customer for your equipment, right? So that's a main takeaway. And of course, wafers per hour throughput of a machine depends on more than just the motion system, but certainly the motion system is a critical component. Okay, so this is my last slide. So the conclusions here is that, again, I'm proud and gracious for the opportunity to present this innovative solution, what we feel is an innovative solution and a potential game-changing solution for stage manufacturers or OEMs that are using stages, precision linear motor gantry stages that's generally employed in next-generation equipment in the markets that I mentioned earlier. And we feel that we're able to achieve some of the performance requirements in these next generation applications that really a traditional motion control system is not able to achieve, just because of the fundamental physical limitations. And then based on the solution that we presented, as discussed, the positioning stages, or a high precision gantry positioning stage, can achieve these levels of performance in terms of accuracy, move and settle, standstill jitter, following error during motion, right, and ultimately lower cost of ownership and cost of goods. These are all benefits that can be realized by by this type of solution. So I think with that, I will hand it back over to Liz. And again, I really appreciate the opportunity and thank anybody that's listened, and certainly welcome any input. If you'd like to email me or call me with any questions, I'd be happy to discuss any questions you have, whether it's commercial, technical, any of the above. I'd appreciate it. So Liz, thank you very much.
Thank you, Jason, for the informative webinar, and thank you to all the participants today, as well as to our sponsors, ACS Motion Control and Micromo. As a reminder, this webinar has been recorded, and an email with a link to the recording will be sent to you shortly. If you have any questions on the presentation material, please feel free to contact Jason directly. Be sure to check out www.motioncontrolonline.org for a list of our upcoming webinars. Thank you and have a great day.